My name is Dan Gross, and I'm a senior developer advocate at AWS. I've been doing development for roughly 29 years or so in different ways, shapes, and forms. I've been with Amazon now for about 4 years and working in the embedded and silicon space during that time. Um, this session's going to be about symmetric multiprocessing, also known as SMP, and it'll be with FreeRTOS and Raspberry Pi Pico. So I'll get into a little bit more about FreeRTOS and the Raspberry Pi Pico, and about this feature known as SMP. All right, so yeah, here's the agenda. So we're gonna go through, like I mentioned, an overview of FreeRTOS, what the project is. We'll talk a little bit about this Raspberry Pi Pico dev board and the chip on it. We're going to talk a little bit about AMP versus SMP as a way to understand what SMP is. And then we're going to go into some multitasking and scheduling that's pertinent to how FreeRTOS behaves with, with embedded systems. And then I'll step through some code examples and some configuration so that if you want to try SMP with your own Pico board, it'd be pretty straightforward and easy to do that. And then I'll walk through some of the SMP specific APIs also that we'll cover, and then go over some resources towards the end. All right. Feel free to ask questions during the session. If anything comes up, I'm happy to just pause and answer questions. All right, so first off, what is FreeRTOS? As the name suggests, it is free, and it is a real-time operating system. It's free in the sense that it's a very permissive MIT open source license. So you can take it, do just about anything with it, license free, and it's been around for over 18 years. Richard Berry started the project, 18 plus years ago, and it's a very widely distributed real-time operating system, and it's downloaded by our data every 170 seconds. It's found on a lot of different products, and it has support for 40 plus different architectures, including ARM v8M, which is the new Cortex M33, and RISC-V also. So there are RISC-V chipsets that support FreeRTOS too. There's a broad partner ecosystem support, silicon vendors as well as toolset vendors, and so forth. A lot of people use FreeRTOS, and it finds its way into a lot of different IDEs and development tools and things like that. I mentioned that it's a permissive MIT open source license. So something to know about FreeRTOS is that it's not just a kernel, it's also libraries. So the whole FreeRTOS project includes both a kernel and core libraries, as well as additional libraries on top of that. You can find the source code at github.com/freertos. So that's where the kernel code is and all the core libraries. And then there's more information at freertos.org. And I think that last bullet there is about inter-process communication capabilities with stream and message buffers. So this is important to understand. Why would you use an RTOS, right? You can program chips like the RP2040 without an RTOS. You can use bare metal. You can use Arduino framework. You can use a lot of different things. But there's different features that come with an RTOS, and some of those are things like queues, or semaphores, or message buffers, things like that. And an important feature is multitasking. So one thing you can do with an RTOS is you can do multitasking. And we're going to talk a lot about multitasking here because it's very relevant to SMP. Okay. So a little bit more about FreeRTOS here. As I mentioned, it's more than just a real-time kernel. It's MIT open source license. We talked about that. It's a real-time kernel. But there are a number of libraries as part of the FreeRTOS project, and we've split those into different repos. And so you have a lot of the core libraries are things like MQTT and HTTP and PKCS11, and even JSON is a library that you can use with FreeRTOS. And those are mix and match. You can use those libraries if you need them. You can bring them in to your project, or if you don't need them, you don't have to use them. And as a matter of fact, they're so generic and plug and play, if you will, that you don't even need to use FreeRTOS the kernel to use them. So you could actually use them with a different RTOS or you know, things like that. So those are known as the core libraries. Now, I forgot to mention that FreeRTOS is a project that Amazon provides stewardship for. So the maintainers are AWS employees. Richard Berry is an AWS employee. He's a principal, senior principal engineer. And so as such, there are a number of libraries for AWS that plug into FreeRTOS as well. Things for connecting to AWS services like Shadow and over-the-air update library and jobs and those types of things. And those obviously are AWS specific. They're under a different organization in terms of the GitHub structure, so they're in the AWS organization instead of the FreeRTOS organization. But those are also generic. You can use them with FreeRTOS or not. But the overall point is that FreeRTOS is not only the kernel, but also all of these libraries. That's what we consider it. And another point about FreeRTOS is that Richard likes to say that it's intentionally unopinionated. So really the idea is that choices are made to be very interoperable with different types of applications, different types of use cases, and really that's about taking the code to the developer using very basic C code and having no library dependencies other than the standard C library. And there's no tool dependencies. Now you may use FreeRTOS as part of say STM32Cube or ESP-IDF or other types of IDEs or tool sets, but there's actually no specific dependency that FreeRTOS has for tools. And this enables different 18-bit, 16-bit, 32-bit, 64-bit architectures. And then here's some of the use cases below of where you find FreeRTOS, fitness or automotive, industrial, mobile, etc. So that's kind of the overview of FreeRTOS. Any questions so far on that? Well, I'll take a quick break. Yeah. Yeah, that's a good point. So actually all of the libraries that encompass FreeRTOS are under the MIT open source license. So they can be used however you like, essentially. I think it is the most permissive open source license. Okay, so, oh, sorry, go ahead. Yeah. There, yeah, yeah. Yeah, the question is about a standard I/O library, and the answer is there isn't a standard I/O library per se for FreeRTOS, but there's one that's actually in I think beta or preview, and it's called Common I/O. And Common I/O, the attempt with Common I/O was to do something along those lines. And so I believe it's out there, and you can take a look at it. But it hasn't been adopted by too many vendors, and so there's work there to be done. And I think it's it would be a great thing to really lift up Common I/O for FreeRTOS for the reasons you're mentioning. But so far there hasn't been a whole lot of support behind that. If you can imagine, a lot of vendors might look at that as why would I undifferentiate my platform, right? Yes. There's not a specific HAL for FreeRTOS, but you might find it in HAL. So for example, STM32 has a HAL that utilizes FreeRTOS, and so there may be hooks in there that you could find FreeRTOS. Okay. Anything else before we move to the Pico? All right. So let's talk a little bit about the Raspberry Pi Pico dev board. So this is the dev board. I tried to just use the standard one on the Raspberry Pi Foundation, but then somebody told me I couldn't use that image publicly. But anyway, so I took a picture of mine on a breadboard. So this is the dev board, and on the dev board is the RP2040 microcontroller. So that's the little silicon square there in the middle, and that microcontroller is really what powers this dev board. It's a 133 megahertz dual core ARM Cortex M0 Plus, and so this is kind of the important part, is that it's got two M0 cores. We're seeing a lot more microcontrollers coming out now that have multiple cores, and so this is a really interesting feature. The other stuff, SRAM and flash, lots of GPIOs on this board, which is nice. A couple of UARTs, a couple of SPI, a couple of I2C. And then the board design files are all open source. So this is kind of nice to look at. If you're going to roll your own board and use the RP2040, you can see their designs. And then we've worked with the Raspberry Pi Foundation to do this FreeRTOS port, and there's demos available for that, and I'll share those links later. But the interesting thing about this port is that we've decided to do the port using SMP, or Symmetric Multiprocessing, and I'll talk about that in a minute. And then the really nice thing is that they have a C++ SDK that they've produced along with a technical specification that is really quite in depth and really nice. It has all of the features you'd expect a hardware SDK to have, and it's available in C. Now, there's a lot of examples for the Pi Pico that use things like MicroPython and Arduino and things like that. But what's really nice is if you want to get deeper than that, if you want to use multiple cores, things along those lines, there's really a lot in the C++ SDK. It's pretty rich, and it's not that hard. That's my personal opinion. Okay, so let's. Yeah, I can. If we have some time later, I can show you my setup. And the thing that I really like about the Pi Pico is that the toolchain is actually really easy to set up. Once you get some of the prerequisites installed, like GCC and Make and CMake and those things in your environment, and I've tried it on Linux and Mac and Windows. And as long as you get your basics set up, it's really pretty easy to bring in that CSDK, bring in FreeRTOS, and you can start writing applications pretty quickly. So let's talk a little bit about AMP versus SMP. So FreeRTOS supports AMP. It has for a very long time. There's a project called OpenAMP that you know, has hooks for STM32 and some of those kinds of chips. And asymmetric multiprocessing, the way to think about that is that each processor core runs its own instance of FreeRTOS if you were to use FreeRTOS with AMP. And so in the diagram here, you can see that we have two instances of FreeRTOS, each dedicated to their own processor core, and they communicate through things like IPC. There's message buffers or queues that you can set up in FreeRTOS so that you can communicate between tasks across those cores, and that's how you would manage that. Now that we've introduced symmetric multiprocessing as a feature for FreeRTOS, what you can do here is take advantage of the fact that there's multiple cores and really just have one instance of FreeRTOS, and it is now aware of the multiple cores and can run tasks across those cores. So so that's the way to think about the two, and both are supported now in FreeRTOS. So let's talk a little bit about multitasking and scheduling, because this is an important aspect of how SMP works. It's a little wordy here. I'll explain it as I go, but essentially, you know, a conventional processor can only execute a single task at a time, and that's if it's a single core system. But by rapidly switching between tasks, a multitasking operating system can make it appear as if each task is executing concurrently. So if you look at the diagram there, and this is a single core instance, we have multiple tasks. They all appear to be executing at the same time. But what would be happening in the case of FreeRTOS is that it's essentially time slicing between ticks those different tasks, right? So say you had 3 tasks, they were all executing. If you look at down at the bottom, there's T1, T2, and so forth. Each of those represent what's known as a tick. And a tick in FreeRTOS determines the timings that the scheduler can bring in new tasks and take them out of the run state. And so, and a tick is configurable for how long it is, but in general, it's somewhere between a millisecond or 10 milliseconds, depending on the chip itself, or how you configure it, I should say. But so the scheduler is then the part of the kernel that's responsible for deciding which task should be executing at any particular time. And so the kernel can suspend or later resume a task many times during its lifetime. And that's what the bottom shows here. And so each of these tasks essentially have the same priority, and the scheduler is essentially just giving them round-robin access to the processing, equally. And so on every tick, it says, okay, task 1, all right, you get your time to execute. Now the tick is over. Task 2, you get your time. So over the course of time, this looks as if these tasks are all executing simultaneously, but they're not. So a little bit more about FreeRTOS task scheduling. This is the strategy that the scheduler uses in FreeRTOS, and the scheduler is an important part of FreeRTOS. The strategy is what's known as a fixed priority preemptive scheduling policy with round-robin time slicing of equal priority tasks. So that's kind of a mouthful, but essentially what that means is that fixed priority, the scheduler will not permanently change the priority of a given task, though it may temporarily boost the priority of a task with priority inheritance. So in general, a task has a priority and it stays that priority unless something changes that. Preemptive, this is an interesting term, and essentially it means that if the scheduler encounters a higher priority task that is able to run, then it will preempt a lower priority task in favor of the higher priority task. So say we have two tasks. One is running, that's lower priority. Even if it's in the middle of, say, a cycle, a tick cycle, the scheduler, if a higher priority task becomes available, the scheduler will preempt that lower priority task to run the higher priority task. And then round robin basically just means that, all things being equal, it just gives every task its turn for entering the running state. And then what we mean by time sliced is that the scheduler will switch between tasks of equal priority on each tick interrupt. And that's unless there's an actual hardware interrupt, and then that would actually prioritize it. So if we look at what the task state machine looks like in FreeRTOS, this is it. Essentially, a task can be in 4 different states, either running, so the task is running, or the task is ready, or the task is suspended, or the task is blocked. And so, yeah, when a task is executing, it's in the running state. When it's not executing, it's in one of the 3 other states. And then tasks that are in the blocked or suspended state, they don't use any processing time. So, this is nice. You see a lot of applications that maybe sit in a for loop or things like that. They can take processing cycles. So it's nice to make sure that you're not taking processing cycles. So the important point here is the last bullet, which is unlike single core microcontrollers and AMP scenarios, SMP now would result in more than one task being in the running state at any given time. So essentially there's a different state machine, or there's different run queues for each processor core. So now that gets a little complicated, right? Because now tasks that you may have thought had a particular order to them based on their priority or based on when they became available to run, now might get a little tricky, because now you have different run queues that the scheduler is bringing into play. So finally, let's just talk a little bit about priorities. So a priority can be from 0 to a configurable number that's configurable in FreeRTOS config.h as that constant there. You can, so the lower the number, the lower priority it is. And idle tasks have a 0 priority. And then there's API calls to set the priority. So when you create a task in FreeRTOS xtask create, you can set the priority there, or later on you can actually use vtask priority set to set the priority. So let's see, the scheduler. That's a convention that's used. V means that it's going to return void. It's not going to return anything. And X means it has something to return. And so in the case of xtask create, it's actually a task handle. So if you look at the FreeRTOS documentation, you'll see that the handle for that task is what that function returns. Let's see, where am I? The FreeRTOS scheduler ensures that tasks in the running or ready state will be given processor time in preference to tasks of a lower priority. So we talked about that. And then finally, any number of tasks can share the same priority. So this is where round robin comes in, right? Okay, so given all that knowledge, let's talk about an example here that uses SMP. So the first thing that we have to do with our Pi Pico is in the FreeRTOS config.h file, and it's many more parameters than this, but these are the important ones, is that you have to first configure the number of cores that you're going to use. And so in this case, we have our Pi Pico here, and it's got 2 cores, so we're going to give that 2 cores. And then in this example, we're not going to run different priorities. We're just going to keep all the tasks the same priority and let the scheduler just figure out when to run each task. And then we have another definition known as core affinity, and I'll get into what core affinity means in a little bit. But essentially, it means which core do you want to run this task on, or which cores do you want to run a particular task on, and that's its core affinity mask, as we call it. So that means that a particular task may only be able to run by definition on certain cores, and so we can set that. And so, do we want to use that configuration? Is the parameter here. So, and then the final 3 are specific to the Pico, but they're not super important. The tick core and then the Pico sync and time interop. So that's the configuration. I'm going to step through just a little bit of code here as a simple example. Essentially, this is a complete application. We're including in the standard, I/O and Pico SDK libraries, as I mentioned earlier. Then there's really just 3 things that FreeRTOS needs. It needs the FreeRTOS.h file to understand the configuration. The task.h, which is essentially bringing in the scheduler into FreeRTOS. And then we're going to use a semaphore here because we're going to do some printing, and there may be some potential collision with our tasks that while we're printing. So that's it. So now we have a task delay and a task size that we've defined, and a mutex, which is our semaphore. Yeah, go ahead. I've got my environment set up so that there's a configuration path that CMake knows about. So I'm building this with CMake, and so that configuration path is known, and so it's not necessarily in the project itself, but there's an environment variable that we set that makes that visible to the tool chain, if that makes sense. Yeah. Okay. So the first function we have is just to print safely, and so we're using our mutex here, this semaphore mutex, in order to print out because we're going to have multiple tasks printing potentially at the same time, and so we want to make sure they don't have a collision. So that's pretty straightforward. We just take the semaphore and give it back. And now this is our main task, and we're going to actually create multiple tasks based on this, and this is the vtasks SMP. And so we're going to get the task handle from this, and this will actually be called later. So in main. So bear with me while we kind of talk through this. But this is the task itself that gets executed. So at first we get the task handle, then we get the core affinity, and so this is one of the new API calls using SMP that lets us get the core affinity for that particular task. So we're in this task, we're getting that mask, and that basically means what cores can we run on. Next we're going to just get the task name, and then we're going to just set up a string to print out, which is the name, the current core number that it's on, and it's getting that this get core num. That's coming from the Pi Pico SDK, and so you can in any given task you can get the core that it's running on, and so that'll come out as either 0 or 1. And then in FreeRTOS, we can get the tick count, so we know what tick we're on. And so I'm getting that, and then printing out the mask. So basically, just this task is pretty simple. It's just essentially letting us know where, you know, what task it is, what core it's running on, what tick it's in, and then what its mask is. And so then it just uses the safe print and then delays itself. And so then this is our main, and this is the whole application from the previous slide and this slide. And so with all the Pi Pico applications using the C and C++ SDK, you have to initialize the I/O. There's where we create our mutex. And now we're going to create 4 different tasks, and they're A, B, C, and D. And task A and task B, we are going to pin, what we call pin, to a specific core. So task A, we're going to pin to core 0, and task B, we're going to pin to core 1. And we do that by getting the handle of that particular task, and then setting the affinity mask, as I mentioned, with that X core affinity set. And so you can see down below there, handle A, handle B are getting set with a different affinity mask. And C and D, we're not setting any affinity mask. So we're basically telling the scheduler here, task A we want to run only on core 0. Task B we want to run only on core 1. But task C and D, you can pick where you want to run them. And then we start the scheduler. So when we start that scheduler, that's when the previous the previous code executes, which is vtask SMP. And so there's 4 of them, and now they're running. Essentially, the scheduler is managing those tasks. So yeah, so if we run through this, and if we have time, I can actually run it on a real Pico, or it might not really look all that pretty, so it doesn't matter. But essentially, if you watch this thing run, you'll notice some interesting behaviors. And I've captured a few different snapshots during the running of this, just to demonstrate a few things that the scheduler is doing here. So the first thing you should notice is that on any given tick, the order of execution and the core that each task runs on can change, right? And this is different from, say, a normal single core microcontroller. But you see that like task D and C, they have this -1 affinity mask, which means they can run any particular core. And you'll see that later on. D is running on core 1 in that first section, and then D is running on core 0 in that second section. And then D is running back on core 1 in that third section. C, on the other hand, yeah, also has been changing where it's been running. You'll see that B and A stick to the core that they're running on throughout, the different sections. But you'll also notice that order isn't necessarily consistent, and this is where sometimes things get a little tricky when you're designing an application using SMP. It comes with a lot of capability. You can see here that on a given tick, you have two tasks, executing simultaneously. So this is the power of SMP. But it also can wreak some havoc on applications that you try to port to SMP without considering when and where that task is going to be executing. So the let's see. So yeah, you can see here, as I mentioned in the bottom section, that each task executes on the core that becomes available. So you know, the scheduler is doing its job essentially, what we know its job to be. But some of this type of behavior we can characterize when you can't quite predict the order of execution. Then this can, you know, we call this non-determinism. So we get into some non-deterministic behavior when we introduce SMP, especially if we don't, if we're not careful with how our application's designed. A lot of our embedded applications will have specific timings or specific order of things for execution. So the thing to be aware of with with SMP is you can increase your processing capacity quite a bit, but you do have to be a little bit careful because things won't always run in the same order. Okay, so getting into some of these specific APIs, they give us a lot more control. So I mentioned core affinity set. So this was where you can set the core affinity mask, and this is you know, essentially the interesting thing here is you can set an affinity mask that is any number of cores. So in the case where we have you know, a system that has even more than 2 cores, say 4 or 8 or 16, and you might laugh and say, well, are there 16 core microcontrollers? As a matter of fact, there are. XMOS actually created a I think 16 core microcontroller that we've ported SMP for, and so you could set an affinity mask that was, say, every even core or every odd core, something like that. And so that's the affinity mask. You can get the affinity mask as we did in our program, and then there's a couple of other API features, which is disabling or enabling preemption. And so this allows you some control for when a task is executing that you don't want it to be preempted. So say it's a lower priority task, it's executing. Now another higher priority task becomes available, but you really don't want it to be, the lower priority task to be preempted by this higher priority task because it's doing something important or whatever. You can use these API calls to control that behavior. Okay. So here's another example where we change things slightly, where we're still using 2 cores. We're running, we're still use core affinity, and but here we're going to run with some multiple priorities, and allow ourselves to control some things. Actually, I'm not sure if this example goes into the multiple priorities, but this is a way that you could configure an application, right? If you were going to get very specific about, you know, the order of execution of tasks. So this one is kind of a contrived example, just a slice of the code, but essentially we're imagining that there's this networking task, and so it's off doing its networking task, you know, stuff, but we want to let's see, make sure that it's always running on core. Oh no, wait. What are we doing here? Oh yes. So, okay. So in this scenario, we assume we have 2 cores, core 0 and core 1. We want to pin the application task. So this is the application task to the core that is not the networking task. So we don't know where the networking task is exactly, but we know there is one, and it's running somewhere. But we want to ensure that that isn't interrupted by our application task. And so here we're trying to understand where that application task is running, so that we can run the application task on the core where the networking task isn't. So that's essentially what this code is doing. And, um, and so you can set up things like this as an example, in your application, so that you can, avoid some of these contentious issues with where and when, code is executing. Okay, so as I mentioned, there's additional SMP support beyond the Raspberry Pi Pico with XMOS. They have this Explorer board. And then ESP-IDF actually has SMP built into it for their dual-core processors in the ESP32 line. So that's the ESP32 and the ESP32S3. And so you can look at using FreeRTOS SMP functions there. Right now, the SMP feature of FreeRTOS is on a separate branch of FreeRTOS in the FreeRTOS kernel, but there's work to bring that branch into main for the FreeRTOS kernel and align with some of the vendors' specific implementations as well, like Espressif and XMOS and TI. Also, I didn't mention, I didn't put them on the slide here, but TI is also working with FreeRTOS SMP. And so all of that is very close to converging, and you will see SMP be part of the standard, the main branch of FreeRTOS. This is an article I wrote for embedded computing design, and it's actually using FreeRTOS with the Raspberry Pi Pico. It's a multi-part series, but part 4 specifically covers SMP and in how to set up your environment. You mentioned you asked how to set up your environment. If you visit this article, it will spell out how to set up your environment, and I can look at that. We can actually pull up my GitHub repo that sets that up too quickly. But and then there's also information about queues and message buffers and semaphores and things like that. And then finally, some more resources. So we do have a page on freertos.org that is all about SMP and FreeRTOS. We have information about how the scheduler works on freertos.org, and there are some SMP demos for the Raspberry Pi Pico board. They're pretty extensive. They get into quite a bit of tests and things like that. So they're pretty nice. And then on GitHub we have the actual demo code, and then there's the Pi Pico SDK, which I encourage you to take a look at. It's a really great resource for the Pico. And that's it for me. Reach out if you like, but